on nuclearity and generalized inductive limits. But first of all, I have to share the couple of pictures that I actually have. So I was not at the conference in '91. I don't think I would have been a very interesting participant then. But nonetheless, I have had some chances to interact with Von, and he definitely made an impression on me. The very first time I met him, he gave a phenomenal series of lectures at the University of Virginia, where I was a PhD student. And unfortunately, this was the tail end of a year-long worldwide tour, and he was exhausted and not exactly the personality that a lot of you guys remember. So then he was just the very intimidating Fields medalist. But then later on, I actually got a chance to meet him in his natural habitat. And here he looks just about as tired, but it's a happy tired because he had been kite surfing all day with Rui in tow. Actually, I think they were windsurfing because Rui was injured. But anyway, the legacy that I really remember of Von is the impact that he's had on a lot of the young people. A lot of the people in this picture are his students, and they all just found it absolutely remarkable the way that he would interact with young people, the way that he would take time and take interest in them, the way he could teach and explain ideas. And he really passed this on to a lot of his PhD students, and a lot of them also share these characteristics. And so it's a little slightly different side of Von's legacy that I got to see, but I'm very, very grateful for the interactions I did get to have with him. Okay, so onto the topic of the talk. Right, so let's just start with a warm-up on some more classical theory. C-star algebras, much like many categories, admit inductive system constructions. So an inductive system of C-star algebras is just a sequence of C-star algebras together with the canonical maps between them being star homomorphisms. And one nice thing that happens in C-star algebras is that we can always form the inductive limit, and that this is actually an interesting object to study. And the construction of the inductive limit is important, so I'll go ahead and mention it. So what we get is, if we take the direct product of the matrix algebras, this is the space of norm-bounded sequences. And then we take the quotient where we mod out by the null convergent sequences. So my notation's different just a little bit from Jill's. So this induces a star homomorphism at the kth step for each k, which sends your a kth C-star algebra into the quotient. And it just goes by taking a single element, looking at the sequence of its images, and then sending that into the quotient. So if you take all of these images, union them up, and then close them off, you get a C-star algebra, which happens to satisfy the right universal properties, and it is the inductive limit. So this construction has provided many interesting examples of C-star algebras. And I will not go into really a lot of the more interesting ones that in particular have played a huge role in the classification program that George was just talking about. Instead, I want to focus on, in a sense, the most basic ones, the AF algebras. So a C-star algebra is approximately finite, or AF, if it's star isomorphic to the inductive limit of finite dimensional C-star algebras. And the example to bear in mind for this is the car algebra, which is where you take 2n by 2n matrices and embed them into the next step by just doubling along the diagonal. So union these up and take a norm closure, and you get the car algebra. So in this picture, we can actually see an AF C-star algebra, well, and also in the former one, is as one that contains an ascending sequence of finite dimensional subalgebras whose union is norm dense. And this has a very important von Neumann analog, which goes by almost the same name. So a von Neumann algebra is called approximately finite dimensional, or AFD, or hyperfinite if you're working in a tracial setting. if it contains an ascending sequence of finite dimensional von Neumann algebras. But now, again, von Neumann algebras are those C-star algebras which are actually dual spaces. So we take the dual topology, so we take the weak star closure of these subspaces. So if I consider the hyperfinite 2-1 factor, it can actually be realized as the weak star closure of a nested sequence of its subalgebras isomorphic to these 2n by 2n matrices. So this is one really nice notion of finite dimensional approximation, which is in general a very important idea in operator algebras. But there are other notions of finite dimensional approximation. One in particular for von Neumann algebra. So Gilles called this, I believe, W star CPAP, and also in the literature it's known as semi-discrete, which basically means for your von Neumann algebra that its identity map approximately factorizes through matrix algebras. So when you say approximately, you need to say what norm you or what topology you mean, and I mean the point weak star topology. And approximately factorizes means that I have this picture that Gilles was describing. There are a bunch of completely positive unital maps. So again, positive maps are ones that send positive elements to positive elements. Completely positive means this stays true under matrix amplification. So you have positive maps that go from your von Neumann algebra down into matrix algebras and back up so that their composition converges pointwise weak star to the identity map. So one good class of examples is the AFD C-star algebras. It turns out to be not too difficult to prove that AFD C-star algebras will be semi-discrete. And the work of Connes, one of the big seminal results of Connes in this direction was actually a converse to this. Any semi-discrete von Neumann algebra is AFD. And this results in variations on it, or I guess more extensions on it, have been described already in various talks here. But this is the one that I want to focus on, at least for the sake of the storyline. So back again, reflecting on George's talk, one of the major outcomes of this theorem was the Kohn-Hagroth classification for injective von Neumann factors. And if you're not familiar with this, let me just give you one really nice corollary to it, which is a special case due to Connes and then taking in Murray and von Neumann's classification of hyperfinite 2-1 factors, is that lots of nice von Neumann algebra constructions are isomorphic to this hyperfinite 2-1 factor. So for instance, if you have a countable amenable group with infinite conjugacy classes, then its group von Neumann algebra is isomorphic to R. Or also this construction that I gave you before with m to the 2n by m to the 2n matrices, it turns out 2 wasn't that special, at least as far as the weak star closure is concerned. As you may have guessed from George's talk, the analogous classification in nuclear setting is not nearly as tidy, and it was really only recently completed after the work of many hands over many years. Now, I'm not saying anything about which side is easier or which side is harder, because they're both very, very deep, sophisticated results. It's just not as easy for me to tell you what the result for the classification of C-star algebras is. Okay, right, so just as AF-C-star algebras are analogous to AFD von Neumann algebras, there is a C-star analog also for semi-discreteness. So we say a C-star algebra is nuclear. Again, this is the CPAP. We say it's nuclear if the identity map approximately factorizes through matrix algebras. But now when I say approximately, I mean with respect to the topology induced by the norm. So again, I have completely positive. Now I don't necessarily need to have a unit around. So we'll take them to also be contractive, at least, norm decreasing maps that, so we have these maps going from A into, really, I could just take a finite dimensional C-star algebra here and then back up into A so that their composition converges pointwise and norm to the identity. And again, it's not too hard to show that any AF C-star algebra will automatically be nuclear. And this is where the analogies start to really break down. Unlike in the Neumann setting, there are many C-star algebras that are not AF. I mean, first of all, there are a lot of non-isomorphic AF C-star algebras. But here are just a few, a lot of C-star algebras that are, a lot of abelian C-star algebras, many C-star algebras arising from amenable groups or their actions, irrational rotation algebras, also the Kunz algebras and Toeplitz algebras. So 3 of these have already been featured pretty heavily in various talks. So a direct analog to Connes' lovely AF is equivalent to semi-finite, or AFD is equivalent to semi-finite is really going to be out of the question for us. But as we can take as a model from the classification program, this should neither be unusual nor a deterrent. Okay, so part 2, generalized inductive limits. So if we want to get an inductive limit description of nuclear C-star algebras, then we need to relax our requirements on the inductive systems, because when we wanted to work with the standard inductive systems that I described from the beginning, we got the AF C-star algebras. So as one works with these inductive systems, you start to realize that on-the-nose behavior at each step, or actually at any step, is really superfluous. And the mantra you should take is that asymptotic behavior is what really matters. And this philosophy is what led Blackadar and Kirchberg to introduce generalized inductive systems of C-star algebras. And here we still take the sequence of C-star algebras, but now we relax our assumptions on the maps. And now we only ask that they asymptotically behave like star homomorphisms. And with this, they actually construct very, very interesting classes of C-star algebras, but I want to focus on one. So I'm going to ignore the full generality of their constructions, where they really systematically relax all the different components of being a star homomorphism. And I want to focus on their NF systems. So an NF system is a sequence of finite dimensional C-star algebras together with asymptotically multiplicative CPC maps. So a CPC map is basically everything you want from a star homomorphism, except it's not multiplicative. If you made it multiplicative, it would be a star homomorphism. So they ask that these be asymptotically multiplicative. So this will be the most technical bit, hopefully, that I have to write. And it means that if you take any k, any finite step along the sequence, and take 2 elements from your kth C-star algebra and a tolerance epsilon, then if you go far enough along the sequence past some threshold m, and then you multiply the images of x and y, and then carry that further along the sequence, then that's the same thing as if you waited until the little nth step to multiply the images of x and y. Okay, there would have been a naive approach here, right? To just say, let me multiply these 2 elements inside of fk, and then maybe far enough down the line, their images get close to, or the image of x times y gets really close to the image of x times the image of y. But again, this goes against the mantra. We don't want to place too much importance on something that's happening at the kth step. So we don't want the multiplication to happen there. Okay, that's just to give you a good feeling for what I mean when I say asymptotic behavior happening in a sequence. Okay, but the thing is, the way that we formed the limit of AF, or the way that we formed general or inductive limits back from the very beginning, that still works now. So the limit of an NF system, we just form the same as before. We get induced now CPC maps from each of the finite dimensional C-star algebras into the product mod sum of the finite dimensional C-star algebras. And we just take the union of all their images and close it up. And that's definitely going to be a self-adjoint subspace. But it turns out that this quotient is actually going to still be a C-star algebra, because the quotient only cared about what happened asymptotically, and asymptotically, things were multiplicative. So we actually do get a C-star algebra, which is called an NF algebra. Since Bruce is here, he can explain where NF comes from. Right, so this...
Yeah, I'll tell you later.
I mean, you give a description in the paper, but it's very, very terse. Okay, so, right, so this is, yeah, it's a bit of paraphrasing, and I know I added an extra criteria, but I want us to really sort of dissect the two major properties that NF C-star algebras have. So a separable C-star algebras NF, if and only if you have a sequence of finite dimensional C-star algebras and CPC maps going from A into the finite dimensional and back. This should remind you of nuclearity, such that for all A and B and A, well, that's exactly the criteria we need for nuclearity. Also, and this is sort of picked up already in this earlier bit, but I want to single it out. These maps going from A into the finite dimensional C-star algebras, they get better and better at approximating the norm of your elements A and A, and they start to get better and better at being multiplicative. And what Blackadar and Kirchberg actually show, Bruce and Kirchberg, it's really funny to call you by your last name when I can see you. Anyway. Right, so a separable C-star algebra is NF exactly if it's nuclear and quasi-diagonal. And just to sort of highlight where these are coming in, nuclearity I already pointed out, and these other two criteria together are exactly what it takes for a C-star algebra to be quasi-diagonal, is to have a sequence of CPC maps into finite dimensional C-star algebras that are asymptotically isometric and asymptotically multiplicative. Okay, so one nice thing that we get is this has given a nice inductive limit description of a lot of really, really nice C-star algebras, in particular ones arising from groups. But there are still some that have actually been very popular at this conference that aren't quite handled by this. Because the thing is, when you introduce a proper isometry, so an isometry that's not a unitary, quasi-diagonality just will not admit this. Taking these multiplicative maps into finite dimensional spaces where all isometries are unitaries just really will not tolerate a proper isometry. And so that means that the Kunz algebras and also the Toeplitz algebra, these can't be quasi-diagonal. So the question is, can we still try to get an inductive limit description of these C-star algebras? Can we generalize these generalized inductive limits? Well, the problem with trying to do that is that if you were trying to drop quasi-diagonality from the inductive limits, that really was intricately tied with the asymptotic multiplicativity that you built in, which is what allowed your systems to be, or what allowed your limits to actually be multiplicative, to be C-star algebras. So if we try to relax asymptotic multiplication assumption from our NF systems, then the limit's only a closed self-adjoint subspace and not an algebra. So we have to be able to relax multiplicativity without losing the C-star structure. And the way that we want to do that is with a very special class of CPC maps. So a completely positive map between C-star algebras is called order 0 if it is orthogonality preserving. And so that means, abstractly put, that if you take two positive elements whose product in A is 0, then the product of their images is 0, even though this map is not multiplicative. So some good examples are, if you take characters, take some homomorphism from C-star algebra into the complex numbers and just weight it by some positive value. Slightly more sophisticated, if I take the multiplication operator from continuous functions on 0, 1 to itself, which is where I just take one of these continuous functions and I multiply it by z, this will also give us a CP order 0. Okay, so
Kristen, sorry, you were frozen for about 2 minutes there.
oh,
Well, not that long.
oh,
1
good.
minute maybe.
Maybe
Yeah.
a minute. Yeah. No,
Can you tell me, was I on this slide or was I on a previous slide?
no,
Yeah, you were on
here.
this slide. You were just
The
starting
second
on this
item.
slide.
The
Okay,
second
cool.
bullet item.
All right, thanks. Sorry, internet is, everyone wants to watch Netflix right now. Okay, thanks. Right, so so a CP, an order zero map is an orthogonality preserving map. It means it sends, if you've got two positive elements that multiply to give you 0, then in the image, they still multiply to give you 0. Some good examples, both of these are really just instances of this last guy. So you can take a multiplication operator where you just multiply by the identity function. This is a CP order 0 map. Take a character from A into the complex numbers, weight that by a positive number or a positive real value. You're going to get an order 0 map. And really what all these examples are is where you just start with a star homomorphism between your two C-star algebras and take some positive element in B that commutes with the image of A. Then multiplying H by pi is still going to give you a completely positive map. Multiplying by a positive element will preserve the positivity here. But since H commutes with the image of A, it's going to get out of the way of this. So that's going to allow us to have an order 0 map. And it turns out that's really all of them. So this is a gross oversimplification of Winter and Zacharias's. Really, it's more of a Steinspring dilation type theorem, but it's a structure theorem for CP order 0 maps. And it says basically just that any CP order 0 map can be written in that form of just some positive commuting element times a star homomorphism. And one nice corollary, which they actually pull from some earlier work from Wolf, is that if I had a CP map from a unital C-star algebra, then it's order 0, if and only if it's almost multiplicative, except one has to pay the penalty of multiplying by the image of the unit. And notice what this means. This means that I probably don't want these to be unital maps, because as soon as a CP order 0 map is unital, it's a star homomorphism. And I've reduced to a nicer setting. But one nice thing about these CP order 0 maps is they still behave a lot like star homomorphisms. So this earlier result of Wolf says that, for instance, the image of a unit commutes with the image of the C-star algebra under an order 0 map. And also from Winter and Zacharias, we know that if you have a CP order 0 map, then all of its matrix amplifications are also CP order 0. So using a more buzzword type term, any order 0 map is automatically completely order 0. And finally, it turns out that if you have any CP order 0 map, so one nice thing that we have about star homomorphisms is you know that if you have a positive element in the image of a star homomorphism, it's got a positive pre-image. And this won't necessarily be the case for CP maps, but for CP order 0 maps, you actually do get this, that given any positive element inside of the image of A, it's got some sort of positive pre-image. And what this lets us say is if you have a CP order 0 map that's actually invertible on its image, then its inverse is automatically CP, completely positive. And by this, I just mean it's mapping positive elements to positive elements on all matrix amplifications in both directions. Actually, if you viewed the image of A under this map, along with the positive structure that it just naturally inherits from B, along with the image of the unit, then you actually get an abstract operator system. So I'm not really abusing the language completely positive here, for those of you who have an eye out for that. Okay, so the really nice thing about this order theorem for CP, or the structure theorem for CP order zero maps, is that a CP order zero map actually really leaves an impression of its structure in the image, even to the point that we can actually detect when just a self-adjoint subspace of a C-star algebra is the image of some CP order zero map. And the reason we can do this is that the structure that it impresses on its image is actually enough to allow us to build a C-star algebra out of the image outright. So I want to really focus on three properties that the image of a CP order zero map has. So let me just take a CP order zero map between C-star algebras, and for ease of notation, I'll set X to be the image of A and E to be the image of the unit. Then E commutes with X. So this was the theorem of Wolff. The theorem of Winter and Zacharias, rephrased, says that for any A and B in A, psi of A times psi of B is just psi of 1 times psi of AB. And finally, we get a nice order unit criteria. What this says is that if you take any self-adjoint element in X, there's some positive scalar such that if I scale E up by R, it'll dominate X. So in other words, E is an order unit. So these are the three features that I wanted to highlight that you get from the image of a CP order zero map. Now let's forget about the CP order zero map and just consider, I'll stick to the setting of closed, self-adjoint subspace, and some positive contraction inside of the ambient C-star algebra, which satisfies those three criteria we just saw. So E commutes with this closed self-adjoint subspace of B, X squared is equal to EX, and E acts as an order unit for X. Then it turns out we can always prove that there exists an associative bilinear map on X and a norm that we can define on X, so that when I take X with respect to this multiplication, which I'll call bullet, and this norm, that is a C-star algebra, and E is the unit of that C-star algebra. And X is automatically going to be closed in this setting. It's automatically going to be closed with respect to this norm. So really, I'm just changing the way that I see X, this self-adjoint subspace of B, and I can see it as a C-star algebra. Because I might switch back and forth between viewing it as a subspace that is not multiplicative and a C-star algebra, we write C-star bullet X when I think of it as a C-star algebra. And what we can actually say even more so is the identity map, which just sends C-star bullet X to X. These are the same thing as sets. It's just I'm viewing C-star bullet X with a different structure on it. This map is actually going to be automatically CP order 0. And it gives a complete order isomorphism between X and C-star bullet. And in fact, if we strengthen 3 enough, then I can guarantee that it's completely isometric, but that's a technicality I'm going to sweep under the rug. Oh, I wrote it on the slide. Good, good. Okay, so these three criteria, in the presence of these three criteria, we can define a C-star structure on this closed self-adjoint subspace of a C-star algebra B. I'm going to abbreviate them all as just C-star. And whenever a closed self-adjoint subspace of a C-star algebra B, together with some positive contraction E, satisfies C-star, then we can define a multiplication on X and a C-star norm on it, so that if you just look at it a little bit differently, it's a C-star algebra. And not only that, but there's a really robust correspondence between X and the C-star algebra. Okay, this feels pretty abstract. What is this C-star algebra? Well, it turns out, by the way that by a special property that the multiplication satisfies, which I didn't get into, if it were unitold, then this would automatically be a C-star subalgebra, and C-star bullet X would just be X. Otherwise, it turns out that there is another canonical C-star algebra to associate to X, and this is the enveloping C-star algebra. It's a minimal C-star algebra constructed around an abstract operator system, which we can view X as. And this other C-star algebra we built will agree with that. And moreover, if X and E arose as the image of an injective CPC order 0 map from some unital C-star algebra, then if that were an injective CPC order 0 map, then A would be the same thing as C-star bullet, would be the same thing as the enveloping C-star algebra. And one other quick note is that it turns out also that E was not so special. If there were another element inside of B so that X and H satisfied those exact same criteria, then the associated C-star algebras would actually be unitally isomorphic. So in a sense, E was very, very special, and then also not. Okay, back to the point. Okay, so remember the whole reason that we were doing this is that I want to relax this notion of asymptotic multiplicative requirements from these NF systems that were defined by Blackadar and Kirchberg. And that's just a reminder of what the definition of NF is. But the issue was that if we dropped asymptotic multiplicativity, we lose multiplicativity in the limit. So the limit need not be a C-star algebra. But now we have a good way to take even just a self-adjoint subspace and know that it corresponds very robustly with a C-star algebra. And right, so remember, I also made this point as well, that if we just start with a sequence of finite dimensional C-star algebras and CPC connecting maps, then we have induced maps into the product mod sum, which I call F infinity because it fits on my slides better. And we can still form the limit just as we did before. This is a closed self-adjoint subspace of a C-star algebra. And though it may not be a C-star algebra, if we guarantee that we can find some positive contraction in F infinity so that X with E satisfies C-star, then I will have a corresponding C-star algebra. So there will be it will be completely order isomorphic to the C-star algebra, C-star bullet X. And not only that, via an injective CPC order 0 map going from C-star bullet X into F infinity, whose image is X, and it's just the identity map. Okay, so I told you when I gave the definition of asymptotically multiplicative that that's as technical as I was going to get, and I will stay true to that. Suffice to say that a generalized NF system is one that encodes within the system those three criteria that gave us C-star. So a generalized NF system is a sequence of finite dimensional C-star algebras with CPC connecting maps and some sequence of positive contractions so that these finite dimensional C-star algebras with the connecting maps in E asymptotically satisfy these C-star criteria. So the reason for the definition is just built to ensure that the limit together with this E, which is the image of the sequence of E ends inside the quotient, satisfy these abstract criteria to guarantee a C-star structure. And then what we can say then is that the inductive limit of a generalized NF system is completely isometrically, completely order isomorphic to a unital C-star algebra. C-star bullet X via this very nice map that I've mentioned before. So again, X is just a subspace, but being, so it's a self-adjoint subspace, and being completely isometrically, completely order isomorphic, that's the gold standard for maps in this setting. Even though we can't get a star homomorphism because it's not multiplicative, this is a very robust map to have. Okay, so the definition still feels pretty abstract. It was also really built to be readily satisfied by our favorite system induced, or by our favorite system, which is one that's going to be induced from a completely positive approximation of the nuclear C-star algebra. So if you combine results of Blackadar and Kirchberg, Winter and Zacharias, Brown, Carry-on, and White, really it's sort of work of Blackadar and Kirchberg through the lens of Winter and Zacharias, but explicitly stated and proved in Brown, Carry-on, and White, interpreted by me and Wilhelm. You can say that any separable unital C-star algebra A admits a completely positive contractive approximation that gives rise to a generalized NF system. Okay, this is a quick sketch of how it goes. So let's take a CPC approximation of a unidal nuclear C-star algebra using this Blackadar, Kirchberg, and Winter and Zacharias and Brown, Carrion, White. I can guarantee that these downwards maps are asymptotically order 0, which should remind you a lot of the criteria that we put for quasi-diagonality, except for instead of multiplicative, I have order 0. So what these do, if you take these downwards maps and just sort of push them into the limit, they're going to give you a completely isometric CP order 0 map from A into the sequence algebra product mod sum of the FNs. So this also is going to induce a sequence between the FNs where we just sort of take the little zigzag here. The problem is just blindly taking the zigzag can introduce too many errors, and you can't guarantee that the limit of this system is going to agree with the image of the map psi. The good news is that if you pass to a subsystem, you can guarantee that things will line up, and that psi of A will actually be the limit of this induced system between the finite dimensional C-star algebras. And the fact that psi is CP order 0 will actually encode C-star into the system. And so X and E will satisfy C-star, and the system will be generalized NF. And right. So again, since X is the image of an injective CPC order 0 map, we have moreover, like I mentioned, that C-star algebra, the nuclear C-star algebra we started with, is isomorphic to the C-star algebra I can build out of X. And then we get really the first direction of the result that we want, which is that any separable unidal nuclear C-star algebra is completely isometrically, completely order isomorphic to the limit of a generalized NF system via some order 0 map. So nuclear C-star algebra means that there's some associated generalized NF system. Right, so on the other hand, the limit of a generalized NF system is just by design completely order isomorphic to a C-star algebra. So the question is, if I just take some generic generalized NF system, do I have any reason to hope that the associated C-star algebra would be nuclear? I know I can associate a C-star algebra very canonically to the system, but can I make it be nuclear, or can I hope it's nuclear? So we already have the beginnings of this, right? We've got these finite dimensional C-star algebras and these induced maps into this space X. And the space X can be completely identified with the C-star algebra, C-star bullet X. Now, it turns out that positivity sort of gets preserved, taking the identity map going the other way. So we can basically just forget about X, and I have these completely positive contractive maps from finite dimensional C-star algebras into C-star bullet X. And that is starting to look a lot like the completely positive approximation property. So the question is, given these upwards maps, can we come up with downwards maps to get a completely positive approximation? Wilhelm, using some of his previous work with Kirchberg, really just flushing out the arguments, can say that if we assume that the upwards maps are decomposable into a direct sum of bounded number of CPC order 0 maps, which you should think finite nuclear dimension here, if you're familiar with that, then the answer is yes, then you can do this. But in full generality, we don't know. But nonetheless, it turns out that this picture actually fits really perfectly into Ozawa and Sato's one-way CPAP, which then tells us that the double dual of the C-star algebra, C-star bullet X, is injective. And then going back through Connes' theorem, part of it that I swept under the rug before, we can then conclude that the double dual is semi-discrete, and then we can actually conclude that C-star bullet X is nuclear. So what that means is that the inductive limit of a generalized NF system is completely order isomorphic to a unidal nuclear C-star algebra via an injective isometric CP order 0 map. And so this is the result of our generalization of these NF constructions of Blackadar and Kirchberg. So Blackadar and Kirchberg could describe all nuclear and quasi-diagonal C-star algebras as inductive limits of these generalized generalized inductive systems, or these NF systems. And by replacing asymptotic multiplicativity with asymptotic order 0, we can drop the quasi-diagonal, and we can say that a C-star algebra is nuclear when it is completely isometrically, completely order isomorphic to the limit of a generalized NF system via a CP order 0 map. And so that was what I had prepared. And thank you one more time to Vaughn for all the kindness that he showed us.
Yeah. So I guess, so we'll open the floor to questions. So if anyone has any questions.
I have a quick question, just to make sure that I understood it right. Thank you very much for a very nice and clear talk. So that means that your theorem now covers cases that have isometries in them.
Yes. So this will cover the cases with isometries.
So okay. Is this sorry for my ignorance, but this is published. This is a preprint.
Oh no, this is ongoing work because we're trying to drop Unital, and we've just about dropped Unital, but needs to be tidied up. So it's still ongoing.
Okay. Thank you.
Okay, well, I could make some comments. First of all, this was a very nice talk and a very interesting results. I could just say a bit about the terminology if anybody's interested. You may have read that before or heard me say it before, but we had a more general class of algebras called MF algebras, and the MF stood for matricial field because well, they were generalized inductive limits of finite dimensional C-star algebras, but it turned out that they were exactly the ones you could put at infinity when you have a space consisting of a sequence of points converging to a limit point to make a continuous field where you just had matrix algebras at the finite points. So we used MF for matricial field, and also to mean Mike Fell, because he was the one who first said that those algebras would be interesting to look at. And then when we went to the NF algebras using completely positive maps, we had nuclear MF. It turns out they're exactly the nuclear MF algebras. So that's where the NF came from. But we also were hoping that it meant nuclear stably finite. And I think that's still an open question. I think a major open question as to whether every stably finite nuclear C-star algebra is quasi-diagonal, or that is an NF algebra. So maybe we should have called them NSF algebras in that hope, but that just seemed a little too shameless. So that's where the terminology came from.
Sounds almost like going from KK to KL.
Well, yeah, it's, I guess, the same idea. Maybe we're not very inventive in our terminology.
Great. If there are no other questions, maybe we could, unmute our audio and then.
I could ask one more question, and that would be: do you think that these results might help in any way in resolving the UCT problem? Because there are no UCT assumptions in any of this work, and so if you have this picture, hopefully maybe it could help there.
Yeah, so the natural first thing to try to go for is to come up with a nice description of an alternative proof of the Connes theorem, right? This would be a good test case. So we've actually already, so this is a recontextualization of a very different project. This is a nice result that came out of a bigger project. And so the next step is really to try to take these systems and be able to encode K-theory in it. And we already have an abstract description of K-theory on these spaces X that satisfy these C-star criteria. We can build the K groups on them, and it corresponds in every way you could possibly want it to with the K-theory on your C-star algebra. Well, the groups themselves at least.
That's a nice advance because we couldn't get to that with our approach. You just really can't compute K-theory from our approach as far as we could see.
We're hoping to submit that, but it's that part is still sort of in its early phases, because honestly, this was a bit of a distraction because we got really excited about hitting nuclear C-star algebras with this construction.
I wonder, could the quantitative K-theory of you and company help?
Yeah, that's, I think Wilhelm has described that as similar to us trying to dig tunnels and meet in the middle. So we both have sort of an asymptotic picture of how we want to be able to describe K-theory in these systems. And theirs is a little bit different than ours, but the hope is that we actually can meet in the middle in some sense.
What about the Tom's Winter class or finite? Can you get that finite nuclear dimension?
I mean, when we're working with finite nuclear dimension, then we can, then the correspondences definitely become much more robust. To be perfectly honest, we've been trying much harder to avoid going to the Tom's Winter class and trying to use more heavily this work of Brown, Caron, and White, where you can actually just describe all the upwards maps as convex combinations of order zero maps.
No.
So the hope is that that'll be enough, and that going to the finite nuclear dimension case won't really be necessary. But yeah, of course, it's good to try to get it to work in the finite nuclear dimension case first, or asymptotic dimension.
Oh, thank you.
Well, in the simple finite nuclear dimension case, as long as you have the UCT, those are already the stably finite ones are in the NF class.
You need the UCT for that?
Yeah. Well, we don't know.
Oh no, well no, okay, but
well, that only comes after the fact, by knowing that from the classification, knowing that they're all, or at least part of the classification, knowing that they're quasi-diagonal. That's all.
Oh, okay.
I mean, that uses at least a large part of the classification theorem, knowing that, all the examples that we exhaust the examples with quasi-diagonal ones, and then we know everything is isomorphic to something of that form.
The UCT seems to keep fading in and out like the Cheshire cat.
Yeah. Of course, the UCT was in the back of our minds when we were doing this, since it didn't come in, but we never got anywhere with it.
Oh, no.
I feel obliged to say that at the Kingston conference, which was, I think, 1980, I'm not sure.
Mm-hmm. Yeah.
When I gave a talk on things to do with the UCT and made at the time just a wild speculation, which I never wrote down, that the bootstrap category was in fact all the separable nuclear ones, because nobody had any counterexamples to that, and I knew nothing about.
Still don't. Yeah.
So, who knows? Coming backwards and forwards, and of course the bootstrap stuff came for the Cooney theorem originally.
Mm.